Hi, everybody. It's Professor Mitchell. We're continuing with Chapter 8, and today we are looking at Section 8.2, testing a claim about a proportion. So in Section 8.1, we went over all of the basics of hypothesis testing, what are all the different things that go into it, and now we're actually going to start doing it. So this section describes a complete procedure for testing a claim made about a population proportion P. We illustrate hypothesis testing with the p-value method, the critical value method, and the use of confidence intervals. The methods of this section can be used with claims about population proportions, probabilities, or the decimal equivalents of percentages. So basically any kind of proportion. There are different methods for testing a claim about a population proportion. In part one, we're going to look at using a normal approximation to a binomial distribution. In part two, we're going to talk about methods that might require the use of technology. So the objective is to conduct a formal hypothesis test of a claim about a population proportion P. So to review the notation that we've already been using, N is the size of the sample or the number of trials. P is the population proportion. P hat is the sample proportion, and that's found by doing X divided by N, where X is the number of people or things in your sample that have the desired attribute or characteristic divided by the total number in the sample. And Q is just 1 minus P. So the requirements for using the normal approximation method are the same as the ones that we talked about back in section 6.6. The sample observations are from a simple random sample. The conditions for a binomial distribution are satisfied. Remember, those are that there are a fixed number of trials. The trials are independent. Each trial has 2 categories of success and failure, and the probability of a success remains the same in all trials. And finally, we have this requirement that N times P and N times Q both have to be at least 5, which means that the binomial distribution of sample proportions can be approximated by a normal distribution whose mean is N times P and whose standard deviation is the square root of NPQ. Notice that P is the assumed population proportion, not the sample proportion. It's easy to get those mixed up. All right, so this is the test statistic that we're going to be using to test a claim about a population proportion. You'll recall in section 8.1, one of the steps was to calculate the test statistic. This is going to be the evidence against the claim in the null hypothesis. So in a world where the null hypothesis is true, your sample proportion is going to have a z-score that's found by using this formula. So notice again, I want to point out, you're going to get the value of P from your assumed population proportion, and that's going to come directly out of your null hypothesis. So there are 2 main approaches to doing a hypothesis test. One is the p-value approach. P-values can be easily found by using technology, or if technology is not available, you can use table A2. Or you can use the critical value approach, and you can use table A2 for that also. When testing claims about proportions, the confidence interval method is not equivalent to the p-value and critical value methods. So the confidence interval method could result in a different conclusion. However, the p-value method and the critical value method will both give you the same conclusion. And the reason that the confidence interval method can give you a different conclusion is that it's based on the sample proportion. The p-value and the critical value methods are based on the claimed population proportion. So the recommendation is that you only use a confidence interval to estimate a population proportion the way we did in chapter 7. Actually, come to think about it, we did not do confidence intervals for population proportions. All right, so we haven't done that before. But use the p-value method or the critical value method for testing a claim about a proportion. So in this section, you're mainly going to see me using the p-value method and the critical value method. All right, so this example should look familiar. 1,009 consumers were asked if they are comfortable with having drones deliver their purchases, and 54%, which is 545 of them, responded no. Use these results to test the claim that most consumers are uncomfortable with drone deliveries. And we interpret most to mean more than half or greater than 0.5. So the claim is that most consumers are uncomfortable with drone deliveries. Remember from section 8.1 that when we state our conclusion, we state it in terms of the original claim. And sometimes that claim ends up being the alternative hypothesis, and sometimes it's the null hypothesis. So we have to be a little careful. So first we'll check the 3 requirements. Number 1, it is a simple random sample. The 1,009 consumers are randomly selected. Number 2, there is a fixed number of independent trials with 2 categories. So success will be the subject is uncomfortable with drone deliveries. Failure will be that the subject is not uncomfortable with drone deliveries. And the requirements that n times p and n times q are both at least 5 are very definitely satisfied. 1,009 times 0.5 is much bigger than 5. So the 3 requirements are satisfied. All right, so first using the p-value method, computer programs and calculators usually provide a p-value. So what you're looking at here is what it looks like on the TI-83 or TI-84 graphing calculator. I believe that you find this function by hitting second variables, VARS. That will bring you to a menu called distributions. So that's something you can play with if you have a graphing calculator. I think what I'm going to do is show you how to get this p-value using StatTrek, although before we use StatTrek, we'll have to calculate the test statistic ourselves. StatTrek doesn't do that part. Okay. And then if technology is not available, we can use table A2. But we'll get to that once we've actually calculated the test statistics. So it's a little early to be talking about that. All right, so going back to the steps that we talked about in section 8.1, the original claim is that most consumers are uncomfortable with drone deliveries. So in symbolic form, that claim looks like P is greater than 0.5. So the opposite of that claim is that P is less than or equal to 0.5. So remember, of those 2 expressions, the one that does not contain the equality becomes your alternative hypothesis, which we symbolize H sub 1. And then the null hypothesis is the statement that P equals the given value. So in this case, the null hypothesis H0 is that P equals 0.5. And the alternative hypothesis, which is the original claim, is that P is greater than 0.5. So we have our null and our alternative hypotheses. All right, for the significance level, we select alpha equals 0.05. I think I mentioned in the last video that the significance level will usually be given. And I still think that's true in homework problems. I don't think they would leave it up to you to select the significance level, because then different people could get different conclusions. In this case, they waited to tell us what the significance level was until they got to this step. So I would say alpha equals 0.05 is probably a good one to pick if they don't give you one. If you end up doing statistics in real life, you have to select your significance level based on how serious an error would a type 1 error be. Because remember, alpha is the probability of making a type 1 error. So if it would be an absolute disaster to reject a true null hypothesis, then you want to make alpha very low. You might want to make it 0.01 instead of 0.05. In statistics class, it's usually given. Okay, in step 5, because we are testing a claim about a population proportion P, the sample statistic P hat is relevant to this test. The sampling distribution of sample proportions P hat can be approximated by a normal distribution. All right, so here is our test statistic. We looked at a little while ago. So we're going to substitute the sample proportion for P hat. And what I almost always do is ask my calculator first, what is this as a decimal? And then I put the decimal there. It just makes it a little simpler for the calculator. The assumed population proportion from the null hypothesis is 0.5. So that goes in for P. And then since P is 0.5, that means Q is also 0.5, N is 1009. So you crunch those numbers and you come up with Z equals 2.55. I want to strongly encourage you to pause the video right now and make sure that you're able to get your calculator to give you this value. Okay. So just really quickly, the interpretation of that Z-score is, in a world where the population proportion is 0.5, a sample that had this large a proportion of consumers uncomfortable with drone deliveries would be more than 2.5 standard deviations above the mean. Okay, that's what that Z-score represents. Because this hypothesis test is right-tailed, and the reason it's right-tailed is because the alternative hypothesis says P is greater than 0.5. So if the alternative hypothesis has a greater than in it, that automatically makes the test right-tailed. It's right-tailed with a test statistic of 2.55. So the p-value, let me, hang on, lost track of my mouse. Okay, so let me show you what this p-value would represent. Here is my normal distribution. And here is a z-score of 2.55. The p-value is the area to the right of z equals 2.55. So it's this area right here. Okay, so there are a couple different ways to find that area. One way is to just use table A2. So let me see if I can bring that up really quick. Uh-oh. Whoops, okay. All right, table A2, let's see, this is probably on the wrong thing. Here we go. Okay, so I'm on the positive side of table A2. I go down to 2.5, and then I go over to the column that has 0.05 on top. And the value that I find is 0.9946. So remember what that means. That is the area to the left of 2.55, 0.9946, which means the area to the right of 0.9946 is the complement. It's 1 minus 0.9946, which is 0.0054. 4. So that's our p-value. What that means is that in a world where the population proportion is 0.5, the probability of getting a sample with a proportion that high is only 0.0054. Okay, so here I am. I'm about to pull up StatTrack. Remember the way I did that last time was I typed Z-score calculator StatTrack into Google. So when I hit enter, the very first result that comes up is normal distribution calculator. So let's pull that up. All right, so I kept this picture on the screen because I thought it would be helpful. If I can see it. Okay, so we're looking for the p-value this time. So we've calculated the z-score is 2.55. And the mean is 0. The standard deviation is 1 because we're working in the normal distribution. So before I hit calculate, let me just remind you that this is going to bring up the area to the left of that z-score. All right, so they've rounded it to 3 decimal places, 0.995. So this is a rare case where table A2 actually gives me a more accurate answer. Okay, so again, we found that the p-value is 0.0054. So that's the probability of getting a sample with a proportion this high under the assumption that p is 0.5. So because the p-value of 0.0054 is less than or equal to the significance level 0.05, we reject the null hypothesis. Remember, when p is low, the null must go. All right, and because we rejected the null hypothesis, that means we support the alternative hypothesis that p is greater than 0.5. Our conclusion is that there is sufficient sample evidence to support the claim that more than half of consumers are uncomfortable with drone deliveries. All right, so now the critical value method. Both methods are the same in steps 1 through 5. It's when you get to step 6 that you do different things. So in the critical value method, we've found the test statistic is z equals 2.55. With the critical value method, what we find are the critical value, is the critical value. What the critical value is, it is a sort of boundary value of z such that any calculated test statistic that is greater than that value will lead me to reject the null hypothesis. Anything that's less, I will fail to reject the null hypothesis. Let me just see, okay. I believe there's a picture of this on the next slide. So with the critical value method, we find the critical value. This is a right-tailed test. So the area of the critical region is an area of 0.05 in the right tail. Referring to table A2, we find that the critical value is z equals 1.645, which is at the boundary of the critical region, as you see here. So the way that I draw this picture is I draw a normal distribution. Because I'm doing a right tail test, I cut off the right tail. The area in that right tail needs to be equal to the significance level, all right? So if you think back to section 6.1, we did a bunch of problems like this. Find the z-score that cuts off the top whatever percent, in this case 5%. So that critical value is z equals 1.645. This green area here is sometimes called the rejection region or critical region. And you see that the calculated test statistic 2.55 is within that region because it's greater than 1.645. Because the test statistic does fall within the critical region, we reject the null hypothesis. And have the same conclusion that we had when we did it with the p-value method. Again, you do not need to use both of these methods in any given problem. Just choose one or the other. In the homework, I believe they will specify which one they want you to use. Okay, really briefly, the confidence interval method. Again, this is not recommended for hypothesis testing, just to show you how it works. So the claim the majority of consumers are not comfortable with drone deliveries can be tested with a 0.05 significance level by constructing a 90% confidence interval. Now, the reason for 90%, let me just go back to this picture. This is a right tail test, which means, and we're doing a 95% confidence level. That means the area in the right tail would be 0.05. Confidence intervals are always two-tailed, which means you also think of there being a lower tail with an area of 0.05. So if you have a lower tail area 0.05 and an upper tail area 0.05, that leaves 90% in the middle. That's why we have to do a 90% confidence interval. All right, so the 90% confidence interval estimate of the population proportion P is found using the sample data N equals 1009 and P hat equals the same thing it was before. The confidence interval is P is between 0.514 and 0.566. So we're 90% confident that that interval contains the true population proportion P. That interval does not contain 0.5, and so this confidence interval would lead us to conclude that the majority of consumers are uncomfortable with drone deliveries. All right, when using technology for hypothesis tests of proportions, we usually enter the sample size N and the number of successes X, but in real applications, the sample proportion is often given instead of X. All right, so an example of that. In the technology I'm using, I don't enter any of that. I have to actually calculate the Z-score. So we may not use this, but a study of sleepwalking or nocturnal wandering was described in Neurology magazine, and it included information that 29.2% of 19,136 American adults have sleepwalked. What is the actual number of adults who have sleepwalked? The number of adults who have sleepwalked is 29.2% of 19,136. which comes out to 5,587.712. So we would round that to the nearest whole number. Using the same sleepwalking data from that example, would a reporter be justified in stating that fewer than 30% of adults have sleepwalked? So again, using a 0.05 significance level to test this claim, let's go through the steps. All right, first checking the requirements, simple random sample, fixed number of independent trials, N times P, N times Q are both at least 5. Okay, so the original claim was that fewer than 30% of adults have sleepwalked. The opposite of that is P is greater than or equal to 0.3. Since the original claim does not include equality, that will be our alternative hypothesis. The null hypothesis will be that P equals 0.3. Significance level is 0.05. Because the claim involves the proportion P, the statistic relevant to this test is the sample proportion P hat. All right, so here they are showing it using technology. I won't spend a lot of time on this. So here is the calculated test statistic using the formula that we used in the last example. Z equals P hat minus P divided by the square root of PQ over N. It seems silly that they would put this fraction here instead of just putting 0.292. because originally they gave me a percentage. We used that percentage to find the 5,588. So it just seems like we're kind of going backwards. I would just put a 0.292 there. So again, check on your calculator. Make sure that you come up with negative 2.41 for the calculated test statistic. All right, this is a left-tailed test because the alternative hypothesis is that p is less than 0.3. So the p-value is going to be the area to the left of the test statistic. Using table A2, I'll assume that you have table A2 in front of you, and I won't flip back to it. The area to the left of z equals negative 2.41 is 0.008. So that's the p-value. What does that mean? In a world where p equals 0.3, a sample that has a proportion of 29.2%, the probability of getting a proportion that low would be only 0.008. So that's a very low p-value. It's lower than the significance level. If p is low, the null must go. So we're going to reject the null hypothesis. There we go, lost my mouse there for a second. Okay, so we're rejecting the null hypothesis, which means we support the alternative hypothesis. There is sufficient evidence to support the claim that fewer than 30% of adults have sleepwalked. Okay, so exact methods for testing claims about population proportion P. What you want to do is identify your sample size, the number of successes, and the claimed value of the population proportion. Then find the p-value by either using technology or binomial probabilities. Okay, so you have your left-tail test where the p-value represents the probability of X or fewer successes in n trials. Right-tail test where the p-value is the probability of X or more successes among n trials. And then a two-tailed test. So we haven't done an example yet of a two-tailed test. So a two-tailed test happens when the alternative hypothesis says that P does not equal a certain value. So what that looks like, you saw this in the last section. A two-tailed test looks like this, and it has a critical region at both ends. So what you need to do then, the p-value is going to be the combined area of these two tails. So the easiest thing to do is just to find the smaller of the left-tailed and right-tailed values and double that. Okay. All right, so here's an example. In testing a method of gender selection, 10 randomly selected couples are treated with the method. They each have a baby, and 9 of the babies are girls. Use a 0.05 significance level to test the claim that with this method, the probability of a baby being a girl is greater than 0.75. So maybe the people who developed this method are claiming that it's more than 75% effective for people who want to have girls. So we're testing that using 10 randomly selected couples. So the reason that this is a good example for the exact method is because I can't use the normal approximation. See, n times q would only be 2.5. All right, so the normal approximation wouldn't give me accurate results. All right, but we can still perform the test. The null hypothesis is that p equals 0.75. The alternative is that p is greater than 0.75. All right, so now you can either use technology to find the probability in a normal distribution, or you can use the formula that we talked about way back in, what was that, chapter 5. Because this is a right-tail test, the p-value is the probability of 9 or more successes among 10 trials, assuming that p equals 0.75. So they've got it here on StatDisk. I think what I might do is also show it to you on Excel. Okay. You could also use table A1 for this. If you remember table A1, we used it a little bit in chapter 5. Okay, so they put in 10 trials. Probability of success is 0.75. So here are all of the binomial probabilities. So what you could do, the easiest way to do it is make this sort of cumulative thing over here, probability of X successes or more. So when X is 9, that probability is 0.244. Or you can't see it because of this red arrow. It would also be really easy to just add this value right here under the red arrow and the value for X equals 10. All right, here I am in Excel. I've just gone ahead and typed in the name of this formula, which is BINOM for binomial, .dist, D-I-S-T. And here it's helping me with the parameters for that formula. The first one is the number of successes, so I'm going to put 9. Next is the number of trials, which is 10. The probability of success is 0.75, and now it's asking me whether I want a cumulative value. I'm going to put true. All right. This is actually the probability of 9 or fewer successes. So that's actually not what I want. I want the probability of 9 or more. So what I'm going to go back and do is change this to 8 using the complement right now. This is going to be the probability of 8 or fewer successes. So there's that probability. And now if I do 1 minus that value, I get the 0.244 that you saw from the StatDisk display. Okay, so we found that the p-value is 0.244. This is a high p-value. What this means is that in a world where this procedure is actually 75% effective, the probability of getting 9 or more girls is almost 25%. So that could easily happen by chance. This is not at all strong evidence that the method is more than 75% effective. So we're going to fail to reject the null hypothesis, which means that there is not sufficient evidence to support the claim that with this gender selection method, the probability of a girl is greater than 0.75. There is not sufficient evidence to support that claim. And that's going to do it for section 8.2.